So deep learning has made a lot of progress in the recent years, and we see this technology in many appliances and devices that we use in everyday life, in language and speech and vision domains. We also see this technology in more high-level tasks like playing games, for example, and even in very critical situations like self-driving cars or healthcare. So I think in these situations it's becoming very important to understand these models and what goes on inside them. Now the progress has been kind of rapid in the past 5 or more years. So this is a performance of an image recognition data set, and I'm showing here error rate, so lower is better. The red bar, the red line is the human level performance, and as you can see, in some cases these systems outperform humans on some benchmarks. We see similar trends in speech recognition. Again, we can outperform speech recognizers in certain cases, and maybe not quite so on machine translation. So this is showing a blue score, a machine translation evaluation matrix. So here higher is better. And we're not there yet, but we're getting close. Now, what's deep learning? People mean different things when they talk about deep learning. As far as this talk is concerned, I'm referring to a class of computational models that process input in a sequential hierarchical order with multiple layers, where each layer generates a more abstract representation of the output coming out from the previous layer. And the building blocks for these models are artificial neural nets, and they come in different flavors. So we have those feed-forward, fully connected networks, convolutional neural networks that are mainly used in vision, and recurrent neural networks that are often used in language and speech. And we'll see different kinds of those used in the talk. All right, so what makes deep learning work? I think there are 3 different reasons why these systems work well. One is obviously a lot of data, and one is massive compute resources, so GPUs. But very importantly, we can train those models in an end-to-end fashion. And that's something that's very important. So for example, here we have on the left a traditional machine translation system. So there are multiple blocks, and you don't need to read inside them. The point here to take is that they are built independently, they do different things, and then they are combined during decoding according to some heuristics. In contrast, on the right, we have a neural network for machine translation that just maps input to output. And input is maybe a sentence in some source language, and output is a sentence in a target language. Now, that may be a very complicated network inside, but all the components of this network are optimized jointly for the task that we care about, which is translation in this case. So that's the end-to-end paradigm. And in speech, we see very similar things. So a traditional speech recognizer may have different modules, things like an acoustic model, a language model, a lexicon. They are built and developed independently and then combined during decoding. Whereas an end-to-end speech recognizer based on neural nets tries to map an acoustic input to some text output. Okay. So more abstractly, we can think of this end-to-end learning as something that maps an input to an output with some neural net that's trained on this mapping jointly. Now that works pretty well in practice, but there are a few problems, one of which is that we don't really know what goes on inside them. So some people think of them as black box, and I'm trying to look inside the black box. So that's the main goal of this work. Okay, so before I tell you how to do that, let's talk about why should we even care about doing that. I think one reason is the kind of deep learning research that takes place now in many places, and I've done that myself. Much of the work into deep learning cares about designing some architecture for some task, evaluating its quality, and maybe we're happy with this quality, maybe we're not. If not, then we'll go back and tweak the architecture, add a nonlinearity, or change the nonlinearity, add a layer, change the dimensionality, all sorts of tricks, and measure the performance again. And then again, maybe we're happy, maybe we're not. We'll go back and forth. That's not a very informed way to conduct research, I think. So understanding these models can help us, hopefully help us develop better systems. There's another reason which I think is very important, and that has to do with how these systems are being used in everyday life. So we want these systems to be accountable for decisions that they make. We want them to be maybe aware of biases that are in the data. And so understanding these systems is important for gaining accountability, especially in places like self-driving cars and healthcare situations and so on. And I think the society is starting to understand that. So the European Union now has a regulation that says that any algorithm must be accompanied by an explanation. It's a pretty broad statement. And people start thinking what to do about it. The IT companies, I think, are struggling with that. But it's happening. So we want those systems to be able to explain themselves, or we want to understand them better. OK. Yeah. So let's talk about the high-level approach. So this is a kind of a standard approach to doing deep learning research. You go back and forth between training an end-to-end system and evaluating.
I'm sorry,
yeah.
Can you go back a slide? I'm wondering whether you would agree that there's at least two very different things going on. One is, you have some loss function, and the developer of the system is trying to figure out how to better, how to change the architecture to better optimize the loss function. And the other one is a user, right? Somebody who encounters this neural network on the road or whatever wants to understand why it just, ran over her bike.
Yes.
Those seem pretty different.
Right. They don't have to be the same. And you can think of mechanisms for explanations that target the latter, the user, and not the former. Or you can think of understanding the former and not the latter. Here I'll be mostly concerned with the former. So gaining a better understanding of what these systems do and not necessarily generating explanations for the users. Although I'll point to that in the future work. And I do think it's an important way to go. Yeah. Other questions? OK. So I'm going to try to depart from this high-level approach of going back and forth between training some end-to-end system and evaluating on some downstream task. And how will we do that? So we'll still start by training an end-to-end system. And this system you can think of as something complex, say machine translation. So we try to map sentences in one language to another language. But what we'll do is think of the trained system as a feature generator. So we can use it to generate features for some language object, for example, words. And those features may be word representations that come from the end-to-end neural network. So these may be outputs of a certain layer in the big end-to-end system. So think activations or outputs of some neural network layer inside. And then we'll take those representations and use them to train another classifier, something simpler, that targets a basic task that we may care about. For example, we may want to classify words into some class. Say, determine what's the part of speech of the word. Is it a verb or a noun, and so on. Or we may want to say what's the sentiment in this word or sentence, and so on. So we'll train a classifier in a supervised learning scenario, evaluate its accuracy on some task, and think of this accuracy as a measure to the quality of the representations that came from the original end-to-end system. And this quality is a way of is a measure for how good the representations are or how good the original system is for the task that we are now studying, the simple task. Okay? And there's a final loop here, which I think is important, which is to use the insights that we gain from this analysis to improve the original end-to-end system. And I think that's something that's tricky to do generally, but I'll show you at least one example where we're able to exploit the insights from our analysis to improve an end-to-end system for machine translation. OK. So the assumption here is that the performance of this classifier, which may be something simple, reflects the quality of the original representations that came from the end-to-end system for the given task that we are now studying. OK. Questions? I see some puzzled faces, Roy.
The last sentence, can you elaborate? What did you mean by that?
About the last step?
Yeah, I mean, how do you induce the performance of the classifier? I mean, can you just...
Yeah, so we have a classifier that takes as input some feature representations that come from the end-to-end model. So think outputs of some layer. And we train it in a supervised learning scenario. So we have a training set, a test set, evaluate the accuracy, for example. And that's the quality of the classifier, but actually it's the quality of the representations. So I'm thinking of this accuracy as a measure to the quality of the original system.
But if you're training, say, a sentiment classifier, and your task doesn't care too much about sentiment, so it will probably not reflect sentiment in the learned representation. Does it mean that it's a bad representation?
It means that this representation doesn't care about sentiment, and that's all it means. I mean, that's fine. I think the power of this method is that you can compare different representations. For example, compare different neural nets, compare different layers, and see what's happening in one layer as opposed to the other layer. Compare different modules that are all inside one big neural network. So it's more in the comparative view. Okay, great. So the outline for the rest of this talk, I'll talk mostly about machine translation and what neural networks for machine translation learn about certain linguistic properties, so morphology and syntax and some semantics. I won't talk about lexical semantics, which is the meaning of individual words, but if someone is interested, I can talk about that offline. Then in the last part of the talk, I'll describe some results on speech recognition and how these models learn to recognize sounds, so phonemes. Okay, so we'll start with MT. Now, machine translation is a field with quite a rich history. It's been around for a while, and there's been a lot of progress over the past 50 years. But only in the last 3 or 4 years, we started seeing neural networks for machine translation really outperform other systems. So by now, the state of the art for machine translation is end-to-end neural network-based models. And these are the objects that we'll study. So how do these work? We break down this black box into 2 components. So we have an encoder that runs on the source sentence at the bottom in some foreign language, maybe Spanish. And that maps the sentence into some representation that goes into a decoder. And the decoder starts decoding the target sentence word by word. So these encoder and decoder are 2 neural nets, and they are connected. So they are trained together in an end-to-end fashion again. Okay, a little more in details. So we read this from the bottom to the top. We have an encoder on the source sentence, and every word in the source sentence is represented as a word vector or a word embedding. So these are real valued vectors that represent words in the vocabulary, and we learn them along with all the other parameters. And there's a recurrent neural network, so a recursive function that goes over the source sentence 1 word at a time from left to right here, and generates some representation for the entire sentence. So these are those circles are, you can think of them as the hidden states or the activations that come out of the recurrent neural network or the outputs of the recurrent neural net at different points in time. And at the last step, we have what we can think of as a summary of the sentence. So that aims to capture the entire meaning of the sentence. And this summary vector goes into the decoder at the top. The decoder takes the summary and starts predicting words on the target language 1 word at a time until it hits the stop sign, at which point we stop. Okay? So that's an encoder-decoder. That works okay. But there's one big problem with this model, which is that we're trying to represent the entire meaning of a sentence with 1 vector. That's a very strong assumption that is maybe not so realistic. And so how can we relax this assumption? Well, what turns out to work well is to look at all the representations of the source sentence, not just the last one, as is happening here. And this is known as the attention mechanism. The idea here is to take those hidden representations of all the source words and combine them with some weighted average. And those weights in the weighted average are learned together with other parameters in the system. So this is called attention because we may have different weights when we try to decode different words. So maybe we have one weight when we decode Mary, a different kind of weights when we decode did and not, and so on.
Sorry, isn't this still a single vector?
This is a single vector, but it's a different vector at every point in time during decoding because of the different weights. That's the important point. So instead of just assuming you have one vector, it's a single vector, but it's dynamically created during the decoding process. Yeah, that's a good point. Okay, so what I'm interested in is those intermediate representations. So hidden states or outputs of a recurrent neural network at some point in time, either on the encoder side or on the decoder side. All right. So just to complete the picture, this is the mathematical formulation of these models. We're trying to maximize the probability of a target sentence E given a source sentence F. We'll do that by factorizing over all the words in the target sentence and computing the probability of each word given the previous words and the source sentence. And all these probabilities are estimated with neural networks, those encoder and decoder, and they have some, the encoder takes some source word embeddings, those are those XIs. It's a recursive function, so it keeps the hidden state, those are the H's that I have here, and updates them during the encoding process. And similarly, the decoder takes the target language word embeddings, those are the YIs here, another recursive function, and another hidden states that are being updated. And then we estimate the probability of the next word given the previous words conditioned on the summary vector. So this may be this weighted sum that comes from the attention mechanism. And finally, our objection function is to maximize the log likelihood of the data using this probability estimates. So this is trained typically on very large amounts of parallel sentences in two languages. So we're talking hundreds of thousands or millions of sentences typically. Okay? All right. So the main research question is what's encoded in those intermediate representations, and more specifically, what's the effect of certain choices that we have when we design the architecture on what these systems learn about language, about properties like morphology and syntax and semantics. So I'm referring to things like what happens on the encoder and the decoder, what's the effect of different layers and the depth, how you represent words, and so on. So there are lots of different things to look at. I'll only show you two here. One is comparison of an encoder versus decoder representation, and the other one is what happens at different layers. All right. So the methodology to study this will be just an instantiation of the high-level approach that I described before. So first, we'll train an end-to-end machine translation system on parallel sentences, example translations. And then we'll generate feature representations using the pre-trained model. So for example, we may look at the hidden representations or intermediate representations of the first encoding layer in this case. So this is a vector that represents the word we in the context as the NMT system cares about that word. And we'll take this vector and feed it into a classifier that tries to predict, for example, parts of speech. Is this word a noun, a verb, or a pronoun in this case? Okay, and then we'll have the accuracy of this classifier as our measure of quality of the representation. Okay, so the first linguistic property that I want to talk about is morphology. And morphology is actually a very important property for translation. So we refer to how you express different verbs, different nouns, and conjugate them in different forms. To give you an example, part of speech is something that just looks at if a word is a verb or a noun, some coarse category. In morphology, we may also be interested in that the verb is a past tense, singular, feminine verb, and so on. And for some languages, like the one that we study here, this is actually very important and affects quality of machine translation systems quite a lot. So we looked especially at languages like Arabic, German, French, and Czech, where morphology is a big deal. And it's very hard to translate into those languages and from those languages. Okay. So the data sets that we used are pretty standard for MT. We used a collection of TED Talks. That's nice because they are high-quality translations and they come in multiple languages. There are lots of numbers here. What I want to highlight is that when we consider the morphology task or part of speech task, there are different levels of richness in the data. So some data sets have a lot of possible tags. For example, in Arabic morphology, we have almost 2,000 tags. But in other cases, we don't have that many tags. Like in some part of speech tag schemes, we just have 30 or so. So what that means is we'll have, if there are 2,000 possible tags, we'll have a 2,000 wise classification task when we try to predict the morphological tag based on the representations. So that's a pretty difficult task. Yes?
Would it make sense to just predict the morphological feature independently?
That's possible. So what I do here is just look at the bundle of features, concatenate them. If you were interested in a fine-grained analysis of, say, only tense or gender, then yes, I think it would make sense. But here, this is like a simplification that we did. Yeah.
How large are your hidden states for your NMT encoder?
Oh, yeah. So we used 500-dimensional hidden states, which is like kind of a standard size for NMT systems.
Okay.
Yeah.
So you can have quite a large number of parameters then in your 2000 classification.
Yes, quite a lot. But fortunately, we have large supervised data sets for this, so for these tasks, so I don't think it's a problem. Yeah. Okay. So regarding this, we did follow a pretty standard regime for training those NMT systems in terms of the hyperparameters and so on. And we do take care to work with carefully split training, development, and test sets to make sure that we're not overfitting things, given this large number of parameters. So we're following pretty standard practice here. Okay. So the first comparison that I think is interesting to do is to look at the representations from the encoder and the ones from the decoder and ask which of them captures morphology or part of speech. Do both of them capture that, or some of them capture that to a better extent? Okay. And that's what we did. So here I'm showing part of speech tagging accuracy using representations from either the encoder or the decoder. So the high blue bars are the encoder and the low orange bars are the decoder. And we have 3 different languages, Arabic, German, and Czech. The way to read this is to understand that there are actually 2 different NMT systems in each language here. So if we consider German, for example, we are interested in studying German morphology or part of speech. So we have a German to English NMT system, and we use that to study the encoder side representation, so of German, when we translate from German to English. And we have another system from English to German, and we use that one to study the decoder side representations, again on German. So in both cases, we are comparing German morphology, and in fact, this is actually the exactly same sentences, so the comparison is fair, but the representations come from 2 different systems, and one time it's from the encoder, one time it's from the decoder. Yeah.
Is it saying there's 90% accuracy on a 2000 rate classification?
So this is part of speech. This is like a 40 or so classification task. If you look at the morphology results, they go down, but there's still a very big gap between the encoder side and the decoder side representations. Yeah. So the main result here is that, or there are 2 main results. One, the performance on the encoder side is quite high. It may not be state of the art, but it's pretty good, relatively speaking. The performance on the decoder side is very bad, actually. These are very low numbers for something like part of speech, and we see similar things in morphology. So a natural question to ask is why? Why is it that the decoder is not learning much about the target language morphology? You would expect that you need to learn something about the target language when you generate sentences in the target language. In the same way that you need to learn something about the source language when you read those sentences and encode them, right?
The decoder state you're looking at, is that for the word you're about to predict? Is that how you...
No, this is for the word that I just read. Yes. Okay. So what goes on here? One explanation that we thought about is the effect of this attention mechanism that I mentioned before. So let's recall how this works. We have a weighted sum over, or weighted average over the source hidden state, and the weights are different during decoding. So if we predict, when we try to predict Mary, maybe there's a high weight on the word Maria in Spanish, just because the 2 are aligned. When we try to predict did, maybe there's a high weight on dio because it's a past tense verb, and when we try to predict not, maybe there's a high weight on no, right? Intuitively, it makes sense that the weights will somehow be aligned in this case. And you could imagine that the decoder can utilize this information from the encoder through the attention mechanism. If we have those weights, the decoder can probably exploit, or maybe can exploit, the source hidden state and doesn't need to learn as much about the target language morphology thanks to this link that the attention mechanism provides. So this is a hypothesis, right? How can we test this hypothesis? What we did is to kill the attention mechanism, so cut the link between the encoder and decoder. So here I'm showing Again, the high encoder results as before, the low decoder results as before in orange, but then in gray, slightly higher decoder results, this time coming from a system without the attention mechanism. So what I did here is force the decoder to learn more about the target language morphology because it cannot rely back on the encoder states through the attention mechanism. Yes?
For the decoder, are you just given a German sentence and you run it through the decoder LSTM, or are you given the German sentence and the English sentence?
I'm feeding first the English sentence through the encoder, and then the German sentence through the decoder, and then ask the classifier to predict morphology.
Okay.
Yep. Yes?
Do you start with pre-trained embeddings to initialize the system?
No, these systems typically don't need the pre-trained embeddings. You could get some gains, but it's not very common to do. Yeah. Okay.
When you observe the quality of the translations, do you find that they're good at morphology? Or, I mean, kind of, I don't know if it's a chicken or the egg, but is it the case that they're unable to generate correctly morphologically correct sentences? Or are they doing great and just it's not being represented in the encoding?
Yeah, so that's a good point. This effect is something that we see even when the translation quality is very good. So it's an effect that's kind of independent from the quality of the translation. So even if you have a simple system that does very well on translation, like French to English, this is a very easy language pair, and you do this comparison, you still see a degradation on the decoder side.
So if the system is able to make the right prediction of the right part of speech tag, then it might be encoding it somewhere else and not in the decoder, or maybe you're just not looking in the right place where this information is.
That's possible, or maybe it doesn't need it. That's another possible hypothesis, which is something that I'll talk about maybe in 2 slides. Yes?
Follow up on Ivan's question. So the decoder state, it's the state after you give it the actual word that you want the morphology for?
Correct.
Not the previous word?
No. But we did try that,
Yeah.
and this actually you get slightly worse numbers.
Even though there's still kind of an intuition there, right? Because
Yeah, the intuition.
state is the state from which you generate.
Right, there's a good intuition there because you try to predict this word, so it kind of makes sense, but it turns out that it's slightly worse. Yeah. Okay, so we see that when you remove the link, the decoder is forced to learn more. We think it's because this link through the attention helps the decoder use the information from the source side. Let's actually test that. What we did is to track the attention weights, find the word on the source side that had the highest attention weight, and add that the representation of that word as more features to the classifier doing morphology prediction on the decoder side. So we'll have now two vectors that go into the classifier. One is the decoder representation. One is the encoder representation of the word that had the highest attention weight. And what we see here in yellow is that the performance goes up again. So this proves or shows that the decoder is able to utilize information from the encoder. The information in the encoder is there, and it tells you something about the target side morphology. And it kind of makes sense because if you think of translation, often you will translate a noun into a noun and a verb into a verb. Not always, but there's some signal there that it seems that the decoder is able to exploit. Matt.
So what vector exactly are you giving to your classifier in the 2 cases previous to this last experiment? So like
Yeah.
you have the decoder hidden state, you have the attended vector, and these get concatenated and then pushed into a softmax to actually output a vocabulary word?
Pushed into the, no. This experiment is to predict morphology.
Right.
So
I'm like the original MT model.
Oh, the original MT model. Yeah, so this is like a standard attention-based model.
Yeah, I'm wondering, what's the vector that you pull out to give to this classifier?
Yeah, it's the it's the hidden state of the decoder. So it does not have the summary, the attention, and it does not have what's called input feeding in translation, so we don't use that. So it's just the hidden state in the decoder.
Isn't there a single vector that then gets like dotted with the vocabulary and you take a softmax?
Yeah, that happens when you predict the.
Wouldn't that vector be better
So I did try to take the vector that is like the summary, which I think is one before that, and you still see a boost, but not above the yellow. So the boost, I think, is between the gray and the yellow. Which I think makes sense. I mean, the yellow is one that targets really the source word that was most important for the decoder.
I guess I would expect that this thing that is actually predicting the next word would be the thing that knows about morphology because it has to actually produce the word itself.
Yeah, that thing does help you more than the default, like the baseline, but not as much as it's just a single hidden state on the encoder side. Yeah, but the intuition makes sense. Okay, so we see that some of the gap we can explain by the role of the attention mechanism, but not all the gap. There's still quite a big gap. And so one possible explanation, one explanation is maybe that we haven't looked hard enough. That's possible, like Roy said. Another possible explanation is that the system doesn't care about that. It just generates translation. The decoder is a good language model and doesn't need morphology at all. And that's what we tried to test. So we wanted to see if we can improve the NMT system using this insight the decoder is not doing well. And what we did is to try to force the decoder to do well on the target side morphology. And we tried several different things. What ended up working nicely is to do multitask learning of doing both translation and target side morphology prediction at the same time. So these are the results that I'm showing here. We have two lines. The blue one is showing blue score. So this is MT performance, higher is better. And the green one is showing morphology accuracy. Again, higher is better. And on the x-axis, we have a weight that governs the loss function on the morphology. So we have a two loss function objective. It's a joint loss. One loss is for translation. One loss is for morphology. If you go all the way to the left, there's only the translation loss. If you go all the way to the right, there's only the morphology loss. So if we look all the way to the right, translation performance is very bad. All the way to the left, translation performance is like our baseline. And then there's a nice spot with a little bit of morphology where we improve the MT performance. So it seems that if you force the decoder to learn morphology, not too much, then you're able to improve the machine translation performance. I think this is a nice example where the insight that we had from the analysis actually make us think of how can we improve the original system. And here's one way to improve the original system. And gain some small benefit in translation performance. Yeah.
This is for a specific language?
Yeah, this is for German. So this is English to German. We also, in that paper, we also tried English to Czech and English to French. This is like our best gain. In the other languages, we also saw gains, but even a bit smaller than this. So the gains are 0.5 or 0.6 blue score is like modest gain in MT. So I think I would say it's reasonable, but not amazing. Yeah.
To use it in practice, you'd have to know what to set the weight to a priori. You're showing the kind of maximum on the curve. So you use a held out set to set the weight, or how do you?
Yes. So this is tuned on these results are on the development set. Or to say it differently, this is the test set results after tuning on the development set.
Right, but what I'm wondering is in practice, right, you tune the weight on the dev set and you wouldn't necessarily find the optimal weight. So the results on the test set, if you had one run, wouldn't necessarily be at the maximum that you're showing given access to the whole curve.
Yes, that's a good point. I mean, this falls into the assumption that the test and the dev distribution are the same, which is often not the case. But it's like an assumption that people do. You could go Bayesian about it and try all weights and integrate over some way, somehow. Or do an ensemble, for example, of different weights. If you're interested in increasing robustness, that may be what I would do. Yeah.
You could also just choose a weight based on the dev set, right? Actually choose one weight and then report the test set results relative to that, right? You're showing here a distribution of test set results.
Yes.
It's, anyway, small detail.
Was the weight higher for more multilingual languages? You did it on multiple languages. Was it about the same weight that you needed, or was it different?
I think we found that about 0.2 is about the weight that we needed for all three languages. it's not a very comprehensive test. It's just 3 language pairs. Yeah.
Quick follow-up on Oren's question. So this is a dev set result or a test set result?
This is a dev set result.
And did you run like that max number on the test set?
Yeah, but I think that, so hold on, let me make sure that I don't make a wrong statement here. No, so I think what happened here is this is the test set results after tuning on the dev set. So this is showing the test set results.
You never tuned lambda on the dev set?
So we try different lambda. No, but I think this is showing test results. I have to go back and check. Yeah.
What was the gold standard for the morphology? All these, all your data sets tags with the morphological information?
So mostly gathered from tree banks.
Okay.
And actually, in the case of the encoder systems, it's easy to just gather that from tree banks. In the case of the decoder results, there's a delicate point here. You have to go through the source sentence and into the target sentence. So we don't have gold annotation on a parallel data set. So what we did is use the morphological tagger and then trained on that. Yeah. OK. So the next point I'd like to show is what happens, what's the effect of the depth of the encoder, or what happens at different layers. And the motivation is that some of these networks are quite deep. So Google Translate now in production is 8 layers on encoder and 8 layers on the decoder. And we're interested in understanding what different layers learn about language. We took a very simple case here of 2-layer system on the encoder-decoder and looked at the encoder side and evaluated representation from different layers. So let me show you the results in a moment. We'll have a couple of different language pairs. We're looking at the encoder source, and we have representations from layers 0, 1, and 2, where 0 is just the word embedding layer, so no context, and layers 1 and 2 are the outputs of the recurrent neural nets on the first and second hidden layers. And I'll show here part of speech accuracy. So before I do that, anyone wants to take a guess what's going to work best for this task, layers 0, 1, and 2? Some people probably know. So Elmo people should not participate in this question. But non-Elmo people can answer. No, let's say, who thinks here it's layer 0 is going to do best? 1 or 2? And what about layer 1? I see more hands. Layer 2? No one likes layer 2. OK, we have 1 layer 2. OK, the layer 1 people are correct. It turns out that layer 1 is slightly better than layer 2. It's better than layer 0. That's expected because layer 0 has no context, and context is something that's useful for these tasks. But the interesting point is that layer 1 is actually doing better. So if you were working on Elmo, you know why that is. So, but if not, what seems to be happening here is that for a task like part of speech or morphology, which is kind of local, lower layers are doing better job than the higher layers. And that leads us to a sort of maybe hierarchy of language properties. So there may be an hypothesis, which is that low-level local properties like part of speech are better represented at lower layers, and global properties or something else is better represented at higher layers. So you could think, if you know the vision analogy, you can think of the CNNs that do vision and how low layers in vision capture edges and how high layers capture objects and scenes and so on. So maybe we can speak of a certain similar hierarchy in language. So, but then on the other hand, we know that deeper networks are doing better. And in fact, the 2-layer system is doing better on translation than a 1-layer system. So something else should be captured at layer 2, right? What is that? So to tell you about that, we need to think of syntax a little bit, and specifically relations between pairs of words. So far, I only talked about word-level properties, part of speech and morphology. What about interactions between pairs of words and more complicated constructions? So what we looked at is 2 cases of dependencies, syntactic and semantic dependencies. So syntactic dependencies are your typical subject-object relations and so on. And semantic dependencies are things like agent and patient roles, so predicate-argument relations. And the two are not the same, right? For example, John wanted to buy apples and oranges. John is the subject of wanted, but it's not the subject of buy. Whereas in John wanted to buy apples and oranges, John is the agent of wanted and also the agent of buy. So two representations they capture different things. Okay, so how can we study that? Well, we want to formulate the problem in a similar scenario. What we did is define a simple dependency labeling task. So we're given two words, for example, John and wanted, and we know that there's some relation between them, but we don't know what relation. And a classifier will try to predict that this relation is a subject relation. And how will it do that? We'll, again, feed a sentence into the machine translation system, take the encoder representations for John and for wanted, concatenate them, and feed that to a classifier that predicts dependency labels. Okay? Yeah?
Are you only considering words that are linked in the dependency graph?
Yes. So it's a very simplistic notion of syntax. We assume that we know the dependency tree, and we just want to label the arcs. And we do that independently. So it's a very, very simplistic notion of how to do syntax. But it's a start, I think. OK. So we use pretty standard data sets for that, for syntax, universal dependencies data set, and for semantic, a semantic dependency parsing data set. And for machine translation, here I use the United Nations corpus. It's a larger data set, and it comes in 6 different languages. So we studied NMT systems that translate between English and other languages and English. And in each case, we will look at the quality of the classifier on predicting those dependencies. OK. So here are the results. There are actually a lot of them, and it's kind of hard to read. But we have multiple language pairs, multiple layers, and even multiple runs to make sure our results are consistent. So instead of just going through all of that, I'll show you average results here. So here on the left, I'm showing average results on English dependencies using NMT systems trained from English to everything else. And on the right side, I'm showing results on other languages. Specifically, we have Arabic, Spanish, French, Russian, and Chinese. And the main trend to note here is that if you go up in the layers, so x-axis is showing layers, the results go up. So higher layers do better on the syntactic dependencies. And that's in contrast to the results that we saw earlier on part of speech tagging and on morphology. So it seems that for syntax, going higher is better than lower layers. OK. Now, that's already a nice finding. It kind of aligns with the hierarchy. But we still don't know why exactly is syntax doing better at higher layers. Let's try to analyze this a little more. We looked at specific relations. So maybe there are certain relations that do better on certain layers than others. Now, there are lots of relations in this data set. So again, it's a little hard to go over them one by one. I'll just highlight a few of them. So on the left, I'm showing the relations that benefited most from higher layers, and on the right, the relations that benefited least. And each point here is the relative improvement from layer 1. So a point of 10, for example, means that layer 2 was 10 points better than layer 1, or layer 3 or 4 were 10 points better than layer 1. So these are delta numbers. And let's focus on the left-hand side for a moment, the relations that benefited most. In some cases, we see quite a lot of benefit, up to 20 or 25 points. These are absolute numbers. And it's interesting to note what kind of syntactic relations get a lot of benefit from higher layers. These are things like lists and conjunctions or clause-level properties, so adverbial clause modifiers. Generally, these are relations that are more loose and longer range than other relations. And if you contrast that to the relations that benefit least on the right-hand side, these are things like determiner, so the relations between the and boy, pretty local typically, or case marking, copula, and things like that. Linguistically speaking, these are relations that are shorter range dependencies, which goes kind of well with our intuition that higher layers should do better with more global properties. Now, we can actually quantify that idea of short and long range dependencies So here I'm breaking down the performance to different distances between words on the x-axis. So a distance of 1 means the two words were adjacent, and a distance of 10 means there are 9 words between them. The trend here that we see is that as you increase the distance, all the performance goes down on all the layers. But what's interesting to note is that the drop is not as big in the higher layers as it is with the lower layers. So the drop is really, really bad with layer 0, just the word embedding, and even with layer 1. But as you go to layer 4, then the drop is not too bad. And that means that the higher layers are really concerned with those long-range dependencies, or they help most with the long-range dependencies compared to the lower layers. Okay, so this was syntax. We repeated this analysis for semantic dependencies, and we saw similar trends. So those are 3 different data sets for semantic dependencies, and in each case we see an increase with the higher layers. So these are the global numbers. Again, higher layers do better, and we also we did the analysis of looking at different relation types and distances and so on, and the trends are very similar to what we saw in the syntax case. So I won't go into them here.
Are there any cases where the first layer does better than anything else when you see a degradation?
Cases where the first layer is better? Yeah, I did not find a case where the first layer is better. I mean for the syntax case, yeah. Yeah, but the point is, yeah, for the part of speech and morphology, the first layer is doing better. Yeah.
Remind me is this an RNN? Is this a CNN? Is this the transformer?
For the NMT system?
Yeah, like these 4 layers?
This is an RNN.
Okay.
Yep.
Did you, by chance, using this new RNN, retry your morphology experiments?
Yes.
And did you see the same boost with the steeper RNN? Like the same?
With the 4-layer one?
Yeah.
Yeah, what you see there on the morphology is that layer 1 is the best. And then there's not really much degradation, not as I saw before, but there's definitely no increase.
It's interesting. So I ran the part of speech experiments for the ML paper, and I also ran some syntax experiments. Not quite the same as you did here,
yeah.
But just predicting for, given only a single word, predict its dependency head type.
Mm-hmm.
So is this a subject or an object or whatever?
Yeah.
And there I saw a pretty strong drop. Like the first layer was better by a lot, also in syntax. So it just makes me wonder, like,
interesting.
How like model dependent is this? Like that you saw in your first experiment this big drop, and the second experiment you saw not a very big drop. These can be so different. I'm just wondering how generalizable some of these are, or if it's really just model dependent. I don't know.
I don't know. So I think you'll have to run a comparison to see, because I have not tried this property of like predicting the head, so I can't say. It could be that the reason we see this increase here is because we're looking at 2 words, as opposed to just 1 word and the head. So I don't know. Okay. So to summarize up until here, we saw that the neural MT representations contain quite a lot of information about different linguistic properties, and we saw a hierarchy of representation that emerges kind of naturally from the data without us providing supervision, where lower layers capture more local properties like part of speech, and higher layers capture more global properties like syntactic dependencies and semantic dependencies. Okay, so the last part is speech recognition and how end-to-end models for speech recognition learn to recognize sounds. Okay, so let's start with some brief history of speech. It turns out that speech recognition and machine translation are actually linked and have benefited each other over the years. They've gone through a similar process, and in the last couple of years, we started seeing end-to-end models for speech recognition that do quite well, although not as well as the traditional system. So I think it's fair to say that the traditional modular ASR system is still the state of the art on many benchmark data sets, but it seems like end-to-end models are catching up, and maybe in the near future, they'll even outperform a traditional system. That's not to say that there are no neural nets inside. This traditional ASR system actually has a lot of neural nets inside. Okay, but we are interested in end-to-end ASR. And in end-to-end ASR, there are actually 2 flavors of models. One is an encoder-decoder model or sequence-to-sequence model, same as we saw before in the MT case. So You take a speech input represented as a sequence of frames, you encode those into some vector, and then you decode the vector into some sequence of text, maybe characters. There's another kind of end-to-end model for ASR, which is called CTC, Connectionist Temporal Classification. The difference here is that you don't condense the representation into one vector at any point in time, and not even with an attention mechanism. Instead, you propagate all the input frames, the speech frames, through a bunch of neural nets and maintain the same number of frames, more or less. And then at the top, you predict characters. Now, there's a problem with this approach, which is the input is typically very long in speech. There's a lot of speech frames, not as many text characters or words. And so you need to do something about that. What CTC does, it sometimes predicts repeated characters. So a bunch of frames may correspond to the same characters. And at other points in time, it may predict blanks, so null characters. So a word like cat, we may want to predict k, and then nothing, and nothing, and then and then t, right? So that's a way to deal with the discrepancy between the very long input and the very short output. And another important point is that there are different ways to think of those, to integrate those blanks and repeated symbols, right? So if I have something like this, this is a different split of blanks and repeated characters, but it also means cat. So what CTC does is that it marginalizes over all those possible alignments, if you want, between a speech input and a text output. So it considers all those possible ways to place the repeated characters and the blank symbols. That's kind of nice. Okay, so a little bit about CTC. This is a model that's been around for 10 years or so, but only recently started being really applied to end-to-end ASR. And what it does is maps an input sequence of speech frames into an output sequence, typically a sequence of characters, again by marginalizing over all possible alignments. And what we want to study here is the output of different layers of this model at different points in time, so corresponding to different input frames. Okay, so the process will be very similar. We'll ask the question, do these models learn phonetics, or how to represent speech sounds? And we'll do that again in 3 steps. First, we train an end-to-end empty system. We use the pre-trained system to generate feature representations for frames, and we train a classifier on those feature representations. And we'll have a supervised learning scenario of classifying frames into phonemes or sounds. Okay. So this is the experimental setup. We use the model developed by Baidu called Deep Speech 2. It's a very deep model made of 2 CNN layers at the bottom, and then a bunch of RNN layers, and then a fully connected layer that predicts characters at the top. And to classify the frames, we use TIMIT, a standard speech data set, where we try to recognize phonemes. So given every speech frame and the representation from a certain layer, we'll feed that to a classifier and ask the classifier what's the quality of recognizing phonemes. Okay? Yeah. So those phonemes are, or phones as they're called in TIMIT, are sounds, things like b, g, d, and so on. Okay. So here are the main results. Here I'm showing phoneme classification accuracy, so higher is better. And on the x-axis, we have different layers, starting with the input frames and 2 convolutional layers, and then a bunch of RNN layers. And you can see this kind of funny-looking line that goes up and down and up and down. That's a pretty strange behavior. Before I explain this behavior, I'll just note that we saw this is a very consistent result that we got with different architectures of the ASR system, different classifiers that we try, different input representation, and so on and so on. So this is a pretty consistent result. But there are 2 interesting points here to note. Well, first, the input features are already pretty good. And you get some benefit from the first CNN layer. So maybe the first CNN captures some variation in the speech input. But then there's a big drop that we should think about. After that big drop, there is a gradual increase with each RNN layer. And that may make sense because RNN layers add more context. And at the end, though, there's a drop again in performance. So two drops that I think is important to explain. Okay, so what goes on here? The first drop is probably given the architecture that in this model, Deep Speech 2, that Baidu used. So what they do in the CNN layers is that they have two layers with strides. That means that they skip some parts of the input or downsample. And this downsampling is good for the speech recognition tasks because it brings you from a very long speech input to a very short text output. But it may be that it comes at the expense of your ability to represent the phonemes. Too much downsampling may mean losing fine-grained resolution that is important for distinguishing certain sounds. And I have some results that show that this effect plays there. It may not be the whole picture, but at least it explains some of it. And the second drop is also very interesting. We see some gradual increase with each RNN layer. Why is there a drop at the end? Here I think it's useful to consider again the difference between the original task and the classification task. The original task was speech recognition, so speech to text. The classification task is to map speech frames into sounds or phonemes. And the two are not the same. For instance, think of a character like C. If we want to predict the character C at the top, we may need to abstract over some phonetic differences. C may be pronounced as K in cat or as S in receive, right? So it's possible that in some intermediate layer it's good to maintain those differences between the different pronunciations, but then at the end, when we really try to predict the character, we want to abstract over that. And so I think it's possible that the very top layers care about the text prediction or the text sequences, whereas intermediate layers care about some speech properties or phonetic properties. Okay, let's go a little bit into that.
About 3 minutes.
3 minutes. Okay, yeah, I'm almost done. So I'm going to skip the strides because I think I already mentioned that. But I'll show you the effect of RNN layers. I think this is an important point, an interesting point to note. So Baidu found that a simple RNN works better on speech recognition than an LSTM. So if you know LSTM, if you don't know LSTM, it's like a more complicated way to do recurrent neural nets. It typically works much better. Why is it that the RNN layer, the RNN works better? So we looked at the comparison on the phoneme classification accuracy. As you can see, there's a similar looking shape. One thing to note here is that the RNN layers actually generate worse representations for predicting phonemes than the LSTM layers. And in contrast, the CNN layers in the LSTM model are worse than the ones at the RNN model. So there's some trade-off between what the recurrent layers do and what the convolutional layers do. When the LSTM has more capacity, it comes at the expense of the CNN and vice versa. Okay. I have some visualizations that I'll skip. I think they're cute, but not super important because I want to talk a little bit about contributions and future work. So the main contribution here is hopefully we gained a better understanding of what goes on inside neural networks for important speech and language tasks. And in one case, we were even able to improve the original system based on the insights. And we discovered this hierarchy of representation that arises naturally in those networks, and I think is interesting and important to think about. In future work, so this goes to Oren's point, I think it's important to move beyond understanding and into explaining why a certain prediction is being made, and that has to do with the accountability of these models. I'm also interested in connections between humans and machines. So we know that in the visual domain, there's interesting connections between what goes on in our brain and what CNN models do. Can we find similar connections in language? And finally, I think everybody wants a better theory to understand these, and so do I. I think especially for analyzing, it will be good to have a better theory for connecting those points. So these are some references. And thanks to my collaborators at MIT and at QCRI, the Qatar Computing Research Institute. And I'll leave you with those contributions. Thank you.